we already seen the importance of surface and its role in altering the properties of materials, especially at the nanoscale. Now, we will take up a formal definition of what is surface energy, what is surface stress, how should you differentiate between these concepts when it comes to liquids vis-a-vis the concepts when you deal with solids, especially crystalline solids, and further how can I go about classifying what are known as clusters, which are small, which are large, and then nanocrystals, and how the shape and other aspects come out naturally when we are talking about clusters and nanocrystals. Now, I may want to assemble a solid or a liquid starting with the gaseous state. In the gaseous state, the atoms are far apart. Of course, they need not be atoms, these entities could also be molecules, but for simplicity here we consider atoms, and we assume that in the gaseous state, since the atoms are far apart, there is essentially no interaction. Of course, there will be collisions as these atoms move about, but the kind of interaction we are talking about is an attractive or repulsive interaction which continuously exists between a set of atoms. And when we want to assemble a solid or liquid, what we do is that we take the gaseous state and put it together in the form of a solid or liquid, which has been shown schematically here. If it is of course a solid, as you can see on the example here, it would be an ordered state where you can see that there is a certain periodicity and order. Of course, I could always assemble an amorphous solid also, but for simplicity we will consider an crystalline solid to start with. In the solid or liquid state, the atoms are typically very close to each other, and this formation of the liquid, and assuming now that I am below my melting point or below the freezing point respectively for the liquid and the solid, then the system would like to lower its Gibbs free energy by being in a state which is the state of a liquid or a solid. Therefore, below the melting or boiling points, I have an increasing energy, and therefore, the gaseous state represents a state of high energy and the solid or liquid state represents a state of low energy. Now, when we assemble a solid, for instance, from the gaseous state, and now this is first what you might call a conceptual experiment we are doing, then we see that of course, the atoms have come close to each other in the solid state, and more importantly this central atom, for instance, is bonded to its neighbors, and in this process of bonding the energy of the system is lowered, and I am specifically referring to the Gibbs free energy, assuming we are working at constant temperature and pressure. Now, but the atoms on the surface, as you can clearly see, for suppose I take an atom here, is only bonded partially compared to its full potential, and therefore, these represents a state of higher energy. Now, when we do a calculation for lowering of energy of the system on the formation of a condensed state, we assume that all the atoms are fully bonded, and you can see that in this process we have done an overcounting, because now we assumed all the atoms are fully bonded while the atoms on the surface are only partially bonded. Therefore, atoms in the surface represent an higher energy with respect to the bulk, and more importantly to keep in mind, the reference state now is the bulk, for instance in this example the crystalline state, and this higher energy state is not with respect to the gaseous or the non-interacting state. And therefore, when I say my surface has an higher energy, what I really imply, it has got an higher energy with respect to the bulk atom and not with respect to the gaseous state, from which of course I started my thought experiment. This is a very important point, often not emphasized on, but it is important to keep it in mind, because now when I say the surface is a high energy state, I should not think that it is in a higher energy state with respect to the gaseous state, and I am assuming that I am below the freezing point now, and it is a purely a coincidence of the fact that I did an overcounting that I have to talk about something known as the surface energy. Suppose I were to do an accurate calculation, in other words, I only count those atoms in the bulk when I try to lower find out how much energy they are lowering, and separately treat my surface atoms and find out how much of energy they were lowered, then I do not even have to consider a concept like a surface energy. But typically this is not how it is done. It is done by assuming that all atoms are bonded well, and then I do a correction with respect to the fully bonded state, which I call the surface energy term. Hence, the reference state for for surface energy is the bulk and not the gaseous state. Now, this automatically implies that it costs energy to put an atom on the surface, and when I am saying put an atom, I take a bulk atom and move it to the surface, then it is going to cost me energy as compared to the bulk. This is the origin of the surface energy, which is typically given a symbol gamma. Now, the surface, since the atoms on the surface have a higher energy, the system wants to minimize the surface area, the atoms want to go closer to each other or in fact into the solid, and this tendency for minimization of area or the tendency to shrink is the origin of what is known as surface tension. We shall see now there is an important caution to be kept in mind, that often surface energy and surface tension are sometimes interchangeably used, but this is not to be done. Now, the origin or the what you may call the seed for this kind of a misconception or a equivalence comes from the fact that suppose I track my dimension of the surface stress or surface tension, it is force per unit length, then it is F by L, and the units turn out to be Newton per meter. The units of gamma, my surface energy, is energy per unit area, which is E by A, energy being in joules, area being in meter square, and joules is Newton meter by meter square. Therefore, units of gamma is Newton per meter, which is exactly identical to the units of surface tension. Just because they are dimensionally identical, we should not think they are identical quantities. Physically, these represent very different type of quantities. Gamma is a scalar, that means surface energy as we know is a scalar, while surface tension is a second order tensor. Further, we will see very soon that how these two quantities are different, or how we should differentiate liquids and solids vis-a-vis with respect to these quantities, what additional quantities and parameters do I need to consider when I am talking about solids and liquids, and more importantly, what is the true origin of this surface tension. So, these are things we will consider next. Just to summarize this slide, we have two important quantities when we deal with surfaces. One is surface energy, other is surface tension. Dimensionally they are very similar or they are identical, but we should note that they are physically very different kind of quantities. Gamma is a scalar and surface tension is a second order tensor. Liquids, in liquids when I am talking, surface energy and surface tension are equivalent concepts and sometimes they can be interchangeably used. But in the case of solids, it is important to note that surface energy is not equivalent to surface tension. Of course, in under very special circumstances they may become equivalent, but for now we will assume that surface energy and surface tension represent different concepts when it comes to solids. Additionally, surface energy could be anisotropic when it comes to solids. So, this is something which is not present in liquids. Liquids, we assume that the surface energy is isotropic, that means it is not direction dependent. Therefore, I need to differentiate between liquid and solid surfaces when it comes to these quantities like surface energy and surface tension, and let us do that next. So, we have a comparison of these solid and liquid surfaces. Now, when I want to characterize a liquid surface, I have a few parameters which I need to specify. I need to specify the two quantities we just now dealt with, the surface energy, which we are given a symbol gamma, the surface tension, which I had given a symbol sigma, and essentially you are characterizing the surface structure itself. The liquid surface structure is characterized by one number, which is the surface density. In other words, number of atoms per unit area which sits on the surface. So, essentially it is very easy for me to characterize a liquid surface because surface energy and surface tension represent equivalent concepts, and I just need one parameter, which is my surface density, to characterize my surface. And this ease is coming from the fact that liquid surfaces cannot support shear stresses. Suppose I apply shear on a surface, then the material will flow, and therefore liquids cannot support shear stresses. So, therefore, we have a term like surface tension. Now, I want to compare this liquid surface with the surface of a solid, then I would note that I could talk about something known as a surface energy, and instead of talking about the term surface tension, I may have to talk about the true quantity, which is surface stress, which is a second order tensor. And in 2 dimensions, it has got 4 numbers or 4 values which need to be specified. Additionally, a surface is also associated with surface torque. The origin of surface torque is related to the fact that the surface energy could be anisotropic. That means that it depends on my crystallographic plane. Suppose I am talking about a crystalline surface, the energy is going to depend on that, and therefore, suppose I am talking about 2 kinds of surfaces. In 2 dimensions, let me call this the 1 kind of a surface vis-a-vis this 0 kind of a surface. The energy of this is expected to be different from the energy of this surface. Therefore, if, and additionally these are of course 2 important surfaces which are called the low index plane surfaces, but I could also have a surface which is close to the gamma 01 surface, or this is now my 01 surface, which I can call a vicinal surface. Now, suppose this is my 01 surface, I could visualize a surface which is inclined to this 01 surface at a small angle. So, I am considering an angle which is small. So, let me redraw this. So, this is my 01 surface, and I am talking about a small angle with respect to this 01 surface, which I call a vicinal surface. Now, since these low index planes are expected to have higher density and they are also typically associated with lower energy, while these kind of high index planes would have higher energy, there is a tendency for this plane to rotate into this orientation. Of course, it really does not rotate, and typically you would find that this would actually break up into steps and terraces, but that is a detail we will not consider now. For now, I will note that this tendency for rotation to a low index direction or a low energy direction is the origin of what we may call the surface torque. Therefore, when I am trying to characterize a solid surface, I need to specify more quantities as compared, and I have to go into a little more detail as compared to liquid surfaces. Now, the first of which we noted was that the surface energy and surface stress are not equivalent concepts anymore in a solid. The solid surface also is associated with a surface torque, and we clearly know that the surface, the surface of a crystalline material has structure and has more numbers need to be specified to characterize a solid surface. Macroscopically, suppose I want to construct a surface from an infinite material, then I need to perform a cut. This cut itself will require 5 numbers to specify. So, for now I will simplify the problem, and I will say, suppose I want to make a surface, then I need a certain orientation at which I need to make this cut, and this orientation can be given by 2 numbers or 2 independent Miller indices in 3 dimensions, and additionally I need to note where is this cut inside a crystallographic cell, and therefore, when I make a cut like this, for instance, a sodium chloride crystal, then I would notice that I would actually produce a polar surface, and depending on where I make the cut, I may have a set of negative charges sitting on the surface, or negatively charged ions sitting on the surface, or a set of positively ions sitting on the surface. Therefore, when I am making a surface in a solid, I need to specify more numbers than I need to specify for the case of a liquid surface, and in a crystalline surface I need to know all the lattice constants. In amorphous phase, if I am not talking about a crystalline substance, I am talking about amorphous surface, then I need to know the density and a short range order parameter. So, in a sense, a solid surface is very much unlike a liquid surface, and that is when I am just even trying to create the surface, for instance. That is what the parameters I was mentioning when you try to make a cut, but additionally after the surface has been created, it will be associated with quantities like surface stress and surface torque, and as we had noted before, a surface in a crystalline solid may undergo relaxation and reconstruction. Therefore, there are possibilities which do not exist in the case of liquid surfaces. In the case of solids, the term surface tension, which is should be avoided, refers to surface stresses. Now, we will see what is the connection between the term surface stress and the term surface tension. The surface energy can be understood, gamma, which we have been dealing with, can be understood as the reversible work required to create a unit area of surface. So, this can be understood, for instance, by using a soap film, for instance, between two sliders. So, I can take two sliders and create a soap film, and assuming this one of these sliders is fixed and this is a soap film, and I can pull this surface, pull this slider here. So, this is my another slider which I can pull, and then see how much work I need to do to create an unit additional area. And suppose I am starting with this area A, and after pulling I may create an area which is, now this new area is A plus delta A. Then I would need to track how much work is required to create an additional unit area of surface, and of course, I will be working at constant volume, temperature and chemical potential with respect to all the species. So, this is an alternate way of looking at what is meant by surface energy. Now, I would like to connect my term surface tension in the case of solids with the term surface stress. Surface tension is the average of the surface stresses in two perpendicular directions. That means that I take my sigma xx component and I take my sigma yy component and average them. That is the term sigma, which I have been referring to as surface tension. So, in some sense, you can think of surface tension as the 2D analogous term to the definition of hydrostatic pressure in 3 dimensions. So, in 3 dimensions we have the concept of hydrostatic pressure, and we know that if you apply hydrostatic stresses on any volume of body, then this body cannot undergo plastic deformation, it can only undergo volume changes. So, we have a 2-dimensional analog of that, which is now my surface tension, which is the average of the two orthogonal stresses. An additional factor comes into play when I am talking about a surface, which is the concept of surface entropy. Now, when I am talking about surface energy, I could just be talking about the internal surface energy, or I could be talking about the enthalpy of the surface, or I could be talking about the Gibbs free energy of the surface. Now, when I am talking about the Gibbs free energy of the surface, I need to involve the concept of surface entropy, and as the surface atoms have higher degree of freedom to move, and hence they have a higher entropy. Though they may have a higher energy, which is tending to, you might call, destabilize the surface or put a surface at a lower stability level than the bulk, but entropically a surface is more stable as compared to the bulk atom, and the competition of the two is going to decide at what temperature I am going to have a stable surface with respect to a bulk. Surface stress at any point on the surface is the force acting across any line on the surface which passes through this point, and in the limit that the length of the line goes to 0. So, this is a way of determining surface stresses, but as we have seen that surface stress can be thought of as the 2-dimensional analog of the hydrostatic pressure, which is a term used in 3 dimensions. So, let me summarize some of the concepts so far. Surface energy is not an energy in itself, it is an energy which comes because of overcounting, and when I am talking about surface energy, I am actually talking about the reference state being the fully bonded state or the bulk crystalline state. Of course, it need not be a crystalline state, it can be an amorphous state or a liquid, but for simplicity we consider a bulk crystalline state. When we are talking about quantities associated with the surface, I need to talk about quantities like surface energy, surface tension, which are dimensionally identical, and additionally I need to involve concepts like surface torque and surface stress. Surface tension itself can be thought of as an average of the two orthogonal stresses, the sigma x plus sigma y by 2, and therefore, it is a 2D analog of the hydrostatic pressure. When I am talking about solid surfaces, I can no longer call the surface energy and surface stress to be representing equivalent concepts, and additionally solid surfaces have a surface torque. And when I am talking about solid surfaces, I may note that the surface might have undergone relaxation or reconstruction, and therefore, the crystallography of the surface could be very different from the crystallography of the bulk. So, some of these points I will just summarize, which you already noted, that liquid surfaces are characterized by a single number, which is surface density. The short range order in liquids is spatio-temporally varying, hence no structure can be assigned to the surface. So, if at all we are going to assign any kind of structure to the surface in a liquid, it is going to be a frozen snapshot of what is happening over a period of time. Crystalline solids have a definite 3D and hence structure in 3D, and hence additional parameters are required to characterize them. The order of this at the surface of a crystal can be very different from the bulk, and this is arising from surface relaxation and surface reconstruction. And even in absence of these quantities, you would expect that the surface is going to be somewhat different from just the bulk termination. Amorphous solids have short range order, but no long range order. Under low temperature conditions and short times, that means we are talking about low atomic mobility regimes, the atomic entity positions are temporally fixed. So, I may have short range order on an amorphous surface, but no long range order, and under typically at low temperatures, I will assume that this short range order persists over long times. Now, we are already noted that crystals tend to have a certain face stud shape, and how can we obtain this shape of a crystal is the next question, and this question is very closely related to the fact that we are considering surface energy. So, we already pointed out that surface energy depends on the direction, that means it is an anisotropic quantity. For instance, suppose I am talking about a 3D crystal, then my 010 surface may have a different energy as compared to a 111 surface, which is expected to have a different energy compared to a 112 surface, which will again be different from every other surface which I can think of in a crystal. Depending on the crystallography or the symmetry, obviously suppose I am talking about a cubic crystal, then the 010 surface energy will be identical to the 100 surface energy, which will be identical to the 001 plane surface energy. So, this is coming from the crystal symmetry. Now, if I grow a crystal, then typically it ends up in a certain polyhedral shape, which is called the growth shape of a crystal. And suppose I now anneal this crystal for long times, then the system will tend to go into its lowest energy state, which is an equilibrium shaped state, in which case the crystal will put out those phases which gives the system overall low energy state. And how do we determine this low energy state of the crystal? In other words, how do I determine the equilibrium shape of a crystal? This is done by a construction known as the Wolf construction. To reiterate, the Wolf construction is going to give us the long time stable state of the crystal and not the growth shape of the crystal, because crystals may grow in shapes which are slightly dependent on the kinetics and kinetics of attachment, etc., and those phases which grow very fast will exhaust themselves. Unlike that, when you are talking about equilibrium shape, it is actually a unique shape which gives the system the low energy state. The way it is done is that we start with the variation of the surface energy with respect to theta. So, we have a polar plot of the surface energy with respect to theta, and you can see that suppose I am considering a fourfold direction in a cubic crystal, then this gamma plot will also have a fourfold symmetry. Another important point to note is that this gamma plot would have certain cusps here, as you can see, which represent low energy surface orientations. Then we draw a radius vector from the origin to intersect the Wolf plot, like for instance OA in the plot. Now, I take my O origin and I draw a tangent and allow it to intersect. Now, the figure formed by the inner envelope of all the perpendiculars is the equilibrium shape. So, you can see if I keep on drawing inner perpendiculars, then I get a shape which is now for instance given by this blue box, and this is my equilibrium shape of the crystal. Of course, this is a schematic here and various crystals would have different kind of equilibrium shapes, which may have 111 surfaces, 100 surfaces, but typically these are low index surfaces which are thrown out by a crystal. A point to be noted is that those low energy orientations obviously are, or the cusp orientations are the more preferred ones, and typically will show up in the what you might call the Wolf construction. So, essential message from this is that because of anisotropy in surface energy, crystals will tend to have polyhedral shapes, and in the case of nanocrystals, because it is surface dominant system, the system would, or the crystal will tend to go towards its equilibrium polyhedral shape in much shorter time scales as compared to a bulk crystal. And of course, we know that most of the bulk crystals we deal with typically could be a polycrystalline material, which means that we are not actually going to get a single kind of a Wolf construction, which we are talking about here. So, Wolf plot gives us the equilibrium shape. From the equilibrium shape, it is of course not uniquely possible to go in the reverse direction and make a Wolf plot. Wolf plots with sharp cusps represent the equilibrium shape, which is typically a polyhedron. If of course the anisotropy is small, then you may not get a nicely festored crystal, as you can see here, with very low number of planes representing the outer surface. The width of the crystal facets goes proportional as the 1 by the surface energy. That means that the largest facets are the ones with the lowest energy. However, the crystal obviously will put out those surfaces which have the lowest energy. Now, we move on to a equivalent, but in some sense distinct concepts, that how do I classify my nanocrystals or clusters based on certain kind of a property. Now, we have seen that we can go to the nanoscale from two possibilities. One, I can make a bottom up approach, that means I start with a few atoms or a few molecules and try to make larger and larger clusters, and at some point of time, if this cluster of atoms or molecules arrange themselves in a what you might call crystalline order, then I can be actually talking about a nanocrystal. So, we will introduce three terms here with respect to properties. One I will call the small cluster regime, one will be the large cluster regime, and of course, I will go into a region which is called the nanoparticle regime, and as we shall see now, that one of the special class of interesting nanoparticles are the nanocrystals or the crystalline nanoparticles. And for now, we will assume that this nanoparticle is a single crystal, that means it does not have further grains into it. In reality, of course, when I am making a top down approach, you might notice that some of the particles could actually be polycrystalline. Now, why do I want to differentiate these three classes, and how is it meaningful in understanding their properties is what we will address next. Later on, we will also take up an alternate way of classifying some of these, because in literature often you would find not only classifications of the kind just now I mentioned, but there are other size regimes which are defined, like people define molecules, people define microclusters, small particles and microcrystals. Some of the regimes and what you might call the property regimes and the definitions would tend to overlap, but depending on the literature you are reading and with respect to certain specific properties, one of these two may be used by an author to actually describe what you might call a cluster of atoms. Now, how can I differentiate my three regimes, the small cluster regime, the large cluster regime and the nanoparticle regime, and why do I want to do that is what we are considering. In the small cluster regime, which could now be in the sub-nanometer regime, the structure and properties do not vary in a monotonic way, and we shall soon see that in this regime we will have certain numbers called the magic numbers when you are talking about clusters. The important point to note, suppose I am changing a property here, which could be a property related to like magnetization, it could be some other property I am talking about, and there is the dotted line here which talks about the bulk value of this property. That means, if I take a bulk material and I measure its magnetization, it will have a certain value. Now, the three regimes which are approximate, of course, here drawn here are these three regimes: the regimes of the small clusters, the regime of the large clusters and the regime of the nanocrystals. In the small cluster regime, if you notice that just by a mere addition of one atom, a property could actually change very, very drastically. Now, this could be, for instance, a stable configuration, this could be an unstable configuration, and hence the property could change very, very drastically by mere addition of one atom or the removal of an atom. So, if you track the property in this small cluster regime, you will see that actually it is undergoing large fluctuations. The nature of these fluctuations and the range of these fluctuations obviously depend on the property, and when we get down to some of the properties, you will be able to see that how actually these properties could vary. But the essential thing here is that I cannot talk about an average property in this case. I have to take each cluster, for instance a cluster of 12 atoms, a cluster of 9 atoms separately, and study its properties, and of course this, as you can visualize, would be a challenging task. I need to first of all separate out these clusters of the same size, then make a measurement on the properties, and any presence of any other size clusters would contaminate my results. In the case of the large clusters, which is basically intermediate between the cluster and the particle or the nanocrystal, there is still fluctuation in the properties, and here we are talking about a size regime. For instance, in the nanometer size regime, there are still fluctuations, but these fluctuations are much more gradual, and typically if you add, for instance, a few atoms or 1 or 2 atoms, you do not expect that these properties is going to change in a very drastic way as it would happen in the case of the small cluster regime. So, here also there is some fluctuations in the properties. Here also you would notice that there are some possibilities of certain sharp minima and maxima, but the overall trend line is not fluctuating that large when you actually add one or a few of the atoms or molecules to the cluster. On the other hand, we expect that somewhere all these fluctuations have to die down, and I have to approach the bulk value of my property, wherein now I do not have to no longer deal with individual clusters like a 30 atom cluster or a 32 atom cluster separately, but I can talk about an average property which of course does not change with size, and that is my bulk limit. But somewhere in the large nanocrystal regime, I would expect that this limit is obtained, and this is of course easy to understand because this is now my what you may call the more monotonic kind of a variation in property. So, here I am not observing fluctuations, the system is slowly tending towards the bulk limit in a monotonic fashion. How many atoms actually constitute a small cluster? How many atoms would I put together to form a large cluster or nanocrystal? Of course, depends on the kind of property I am studying and the kind of system I am considering. So, for instance, suppose I am talking about as we consider the magnetic property, ferromagnetic property, and I am talking about nickel atoms, this variation could be different vis-a-vis. For instance, suppose I am talking about some totally different property like for instance the corrosion resistance or oxidation or adsorption of a foreign molecule vis-a-vis some other particle like a iron particle. The intermediate regime is a regime where I would presume that the crystalline order has not yet been established. In small clusters, there are not even sufficient number of atoms to even talk about, for instance, a long range crystalline order, because when I am talking about a crystal, I am assuming that at least there are a few tens of unit cells or a few hundreds of unit cells in each dimension, and this long range order, which I call a crystalline order, has been established. But in the case of small clusters, it is meaningless to talk about it. In the case of nanoparticles, which is now also, as we can consider an example of nanoparticles, the crystalline state, there it is clear that I have enough number of unit cells to classify that as the nanocrystal. In the large cluster regime, this is some sort of a gray area where I perhaps do not have enough number of atoms or unit cells to classify that as a nanocrystal. These large clusters may be crystalline in some sense that they may not represent just a polyhedral shell, but in this toward this end they may actually have a few unit cells. But along the way you would notice that the structure might change from that of some kind of a cluster behavior where I have no kind of unit cell formation to a regime where you actually have a crystalline structure. Here, though we are not explicitly talking about the structure, we are actually talking about the property, but it is very clear that this property would be a sensitive function of the structure, and therefore, it is meaningful for us to correlate the structure with the property we are talking specifically. So, to summarize this slide, there are three regimes which we can talk about, which is a small cluster regime, the large cluster regime, and the nanoparticle regime. And the specific examples of nanoparticles we are talking about here are nanocrystals, and for something to qualify as a crystal, we should have a sufficient number of unit cells, so that a long range order has been established. In the small cluster regime, which is in some sense a very interesting regime, a mere addition of one particle or one atom or one molecule can actually lead to a drastic change in the properties, and these fluctuations with respect to size would die down in the large cluster regime, wherein the oscillations become smaller, and of course, in the bulk in the nanocrystal regime it becomes monotonic. So, let us now talk about going from clusters to nanocrystals a little further. Clusters are aggregates of atoms. Of course, they could be aggregates of molecules or ions also, usually less than a few thousand atoms. So, when I am talking about clusters, typically I am dealing with a less than about few thousand atoms. Typically, when the term cluster is applied to a collection of small number of atoms, so we do not use the term cluster for large collection, for instance, in the case of a nanocrystal. The structure and properties of clusters are often very different from the constituent atoms and their bulk counterparts. So, this is something to be kept in mind. For instance, suppose I could be talking about a material which is anti-ferromagnetic in the bulk, but which could turn ferromagnetic in the small cluster regime. Therefore, there is a drastic change in properties which are possible when I go to the cluster regime as compared to the bulk counterpart. If the cluster is made up of molecules, the individual molecules themselves could have a certain kind of a property, but the property of the cluster could be very different from the property of the individual molecule or the constituent atoms. At this level of the cluster, there is not sufficient atoms to classify it as a crystal, as we saw, because there are insufficient atoms to establish this long range periodic order. If an atom is added to a small cluster of atoms, reconstruction usually takes place. I mean reconstruction with respect to the structure, which is a rearrangement of the atoms, and we have seen that this implies that the properties of two clusters which are close to each other in terms of number of atoms could be very different, and this is what makes the study of these clusters very exciting. At a certain larger size, the critical size, the bulk structure will be established. When we mean a bulk structure, we already seen we are referring to the bulk structure not only in terms of the tangible kind of a definition, but here we are actually referring to it in terms of the property based definition. Small metal clusters, for example, on substrates assume icosahedral, bipyramidal, etc. kind of shapes, and obviously these icosahedral and bipyramidal shapes do not represent crystals. In many cases, the size reaches about 150 nanometer, the crystalline structure is obtained. That means that now in the small cluster regime, there are certain polyhedral shapes which are not crystalline, or they are just clusters. When you reach about 150 nanometers, you obtain the large bulk crystalline limit, and in between the two, you could actually be stabilizing, for instance, different kind of crystal structures which are not the bulk crystal structure. So, let us summarize some of the aspects we have seen with respect to clusters and nanocrystals. The shape of nanoclusters and also nanocrystals can be very different from their bulk counterparts. And now we are talking about the shape of the external polyhedra which forms in the equilibrated shape, which we have seen that how we can obtain from a Wolf construction, but a Wolf construction typically applies to large crystalline macroscopic tangible bulk kind of a crystal rather than to these small clusters. And therefore, I may have Wolf construction for the nanocrystal or the bulk crystal, and I may have these clusters, and these two shapes typically are very different. Large crystals may adopt large clusters, and of course small clusters may adopt a crystal structure. Now we are talking about large clusters, because in the case of small clusters we cannot even talk about a crystal structure. The large clusters may adopt a different crystal structure as compared to the stable bulk crystal structure. So, this we have noted already, and we will also see examples of phase transformations later on, wherein when we reduce the crystal size, we see that new phases are stabilized. We already seen couple of those examples in the case of Fe2O3, etc. Given the large surface to volume ratio, the equilibrated shape can be attained quickly in nanocrystals and also in large clusters. So, if I have a shape which is when I am synthesizing a solid or it is produced by a certain method and it is not the equilibrium shape, it can reach the equilibrium shape very quickly. Now, we will see next that a certain magic number of atoms may be stabilized in clusters, and we will also see what is the origin of these magic number of atoms. In other words, when I am talking about a cluster, the cluster, instead of behaving like a collection of individual atoms, tends to start to behave like something like a super atom. That means the entire cluster itself can be visualized as an entity in itself, which can be thought of as a super atom. And not only that, these nanocrystals themselves may serve as motifs in higher order hierarchical construction of crystals, and we will take up some examples wherein, of course, in many cases you have what is called self assembly, wherein I start with a nanocrystal and then use this as a motif in making a larger unit crystal, wherein of course I am not worried about the ordering of atoms within this nanocrystal, but I am talking about ordering of the nanocrystal themselves in a periodic fashion to give rise to a what you might call a crystal of an higher order. So, I can have an hierarchical construction of crystals, and this is a very interesting concept which we will explore further. One interesting example, we talked about shapes of crystals, and when we are talking about a shape of a crystal, we are typically assuming that is arising naturally from some kind of a polyhedral arrangement. But if you look at some of the examples, like for instance, I am here showing a multiply twin gold nanoparticle, a schematic of that which is about 35 nanometers, and we have talked about this kind of a structure with respect to what we may call a rotational twin. So, we had given this as an example of a rotational twin. Suppose I have twinning occurring in a bulk crystal. So, typically some of these twin boundaries would exist, go in a, for instance, in a copper crystal would extend from one grain boundary to another. So, let me draw that schematically here. Suppose I am talking about a copper polycrystal. So, I have a grain structure like this, and I may notice that within a single grain you may have one twin boundary and of course, another twin boundary extending from one grain boundary to another. So, suppose I have crystallographic planes here. These crystallographic planes would be reflected here by this, and this other twin would actually restore my orientation. So, this is of course twinning in a polycrystalline material, but many a times this kind of twinning would lead to internal stresses in the material. But in the case of a nanoparticle, because the way these arise and the fact that they are not embedded in a matrix, actually these stresses could not be large, and you could actually stabilize a nanoparticle which is having, for instance, in this case a 5-fold rotational twin. Now, of course, we had noted in that context of these rotational twins that if I were to put a selected area diffraction aperture here, I would mimic a system of higher symmetry. In fact, I would think as if there is some 5-fold symmetry arising from this kind of a twinned particle. The two variants in an ideal circumstance in such a crystal could be related to a 72-degree rotation. The 72-degree of course is an ideal kind of rotation I am talking about, and if you refer to some of the publications, you would notice that the actual angles involved could be close to 72 degree, but they may not be exactly 72 degree. For instance, they could be 71.2, etc., etc. So, they are close to 72 degrees, giving this some sort of a close to a 5-fold rotation. In twinning of a diamond film, for instance, the angles have been found to be again close to about 72 degrees. But the interesting thing here is that in systems wherein I am talking about twin as a defect in a perfect crystalline order, they could be much more easily stabilized in the case of nanoparticles. In fact, in many nanoparticles we will see that the deformation mode will switch from that of what you might call a dislocation plasticity to a twinning kind of a plasticity much more easily. And this is some good feature that we have in nanoparticles and nanocrystals, that certain defects are much more easily formed, and some of these defects may not be found in their bulk counterparts. And additionally, of course, you may have gold nanoparticles about 20 nanometer which can form with an icosahedral shape. So, we know that icosahedral symmetry is not compatible with translation, but still you find nanoparticles which can have these kind of a shape which is otherwise not seen for bulk crystals. So, with respect to crystal structure, with respect to properties, with respect to defect structures within the material, we may note that nanoparticles and nanocrystals and nanoclusters could be very different from their bulk counterparts. And this is something which is very important for us to note. We had stated initially, when we consider the classification of nanoclusters or small clusters vis-a-vis large cluster vis-a-vis nanoparticles or nanocrystals, that there are alternate classifications used in literature, and we had even noted when we tried to make the assembly called a cluster that we need not start with an atom, we could actually start with an ion, or we could even start with a molecule, and therefore it is for us good to revise certain other classifications which are typically found in literature. One of them is shown here, wherein a slightly different terminology as compared to what we have just considered is introduced. In some sense, the microcrystal which is mentioned here is very similar to our nanocrystal in some sense, but the size regimes could be overlapping with these, but may not be identical with what we are classifying here. So, we could be starting with molecules, and here we are talking about individual molecules like CO2, it could be O2, etc. Then we go to the regime known as the microclusters regime. Then we have the small particle regime, and you may notice that the microcluster regime is similar to our what you might call the small cluster regime. And the small particle regime can again be somewhat coincidence with the large cluster regime, and microcrystals, as you can see, are much larger, wherein you have about 10 power 6 number of entities. So, we have said atoms here, but we should again note once again that the constituent entities need not be atoms, they could be ions or molecules. So, for molecules it is about 1, for microclusters it is about 10 power 2 to 10 power 3 entities. For small particles it is about 10 power 4 to 10 power 5, and larger than 10 power 6 can be thought as microcrystals. The radius in nanometers for microclusters is about 1 nanometer, or it could be sub 1 nanometer, and small particles are about 10 nanometers, and microcrystals are larger than 50 nanometers. When you are talking about bonding characteristics or the atomic arrangement, molecules, of course, you have their usual rule of bonding. In other words, they could be covalently bonded, or the bonding could be polar covalent, etc. In microclusters, the surface and interior atoms have behavior very different from bulk atoms. Now, I am comparing the surface atom sitting in a microcluster and the interior atom in a microcluster with what you might call a bulk atom in a bulk crystal. And I am talking about a bulk crystal, I am considering something having more than about 10 power 6, maybe 10 power 8, 10 power 10 kind of an atoms, or even larger number of atoms. So, here the surface is different from the surface which we can think of in a bulk material. The interior atoms are also going to be different compared to that what we see in the case of a bulk crystal or a bulk particle. In small particle regime, their interior atoms are similar to bulk. That means they have already grown so large that their overall what you might call environment and configuration is somewhat similar to the bulk interior atom, but definitely not identical. But the surface atoms still behave very differently, because still suppose I am considering a small particle, still I cannot ignore the curvature effects, and sooner during this course of these lectures we will see that how surface effects can alter the equilibrium between a matrix and a small particle, and this is the origin of what you might call the Gibbs-Thomson effect. But essentially the surface atoms still are very different from the surface atoms in a bulk crystal, wherein of course curvature effects can be ignored. In microcrystal, surface is still an active site, but this can be approximated to the surface of a bulk crystal. When I am talking about electronic properties, for instance, and of course I can go on in the list of properties which I am going to consider, but for now I am going to just talk about this as an example, electronic properties. The energy levels are discrete, of course, for a molecule. We know how a molecular energy levels are, they are similar to an atomic energy level. In the case of microclusters, the valence electrons exhibit shell structure with magic numbers. So, we will return to this concept very soon, wherein I am talking about certain magic numbers and certain kind of a stable electronic configuration. But nevertheless, here too I do not expect any kind of a continuous band formation, and still the energy levels are discrete. In small particles, still quantum size effects are going to dominate, and in the micro crystal level, you would expect that you can now talk about more like continuous bands, which you talk for a bulk crystal, and therefore you could talk about conduction properties, for instance, which is very similar to that of a bulk crystals. But here too you would expect the surface plasmons are playing a dominant role, and similarly other surface effects coming from electrons on the surface is expected to play a dominant role in determining the properties of the material.